Section 10. Please turn to page 112 of your Canadian Electrical Code book. Section 10. Grounding and bonding. Just for your information, the photo on the left is ground fault indicating lights installed on a Delta system. The photo on the right is an impedance grounded system, also known as a neutral ground resistor, for the secondary of a 13.8 kV high voltage transformer. Section 10 Overview. Section 10 has been reorganized and significantly reduced in size. Question: what do you think happened to the other 7 pages of Section 10? Where do you think they went to? See Appendix B. Tables 16A and 16B have been deleted and recombined into a new Table 16 with Rule 10.614 providing specific conditions for selecting the size of bonding conductor or bonding jumper. For an excellent explanation on grounding and bonding, please read Rule 10-002, but in brief. Grounding. Its intent is to reduce the shock hazard between earth and non-current carrying metal parts on equipment and limits the voltage rise on the neutral conductor. Bonding. Bonding conductors carry fault current and equalizes the ground potential rise between different pieces of electrical equipment. A small overview on Section 10. In the prior 2015 Canadian Electrical Code, Section 10 consisted of 15 pages and 3 tables. The 2018 Canadian Electrical Code has been reduced to 8 pages, and technically it's 1 table, so that's Table 16. Table 41 has actually been amended and applies to mobile homes, Section 70. Section 10 has also been reorganized into a more logical flow. Tables 16A and 16B have been deleted. Tables 16A and 16B have been recombined to form a new Table 16. And once again, please read the Appendix B note for additional information. Also, a special note, as you're well aware, the delta triangle symbol represents a change. If you notice in Section 10, there is only one triangle, and that is right at the beginning of Section 10. That's to reference that the entire Section 10 has been revised. Just to go back to the prior 2015 edition of the Canadian Electrical Code, Section 10 consisted of scope and object, system and circuit grounding, grounding connections for systems and circuits, conductor enclosure bonding, all the way up to 10-1100 installation of neutral devices. In the 2015 Canadian Electrical Code, and as shown here, there were 12 subsections within Section 10. In the 2018 Canadian Electrical Code, and as shown here, there are now 8 subsections within Section 10. As indicated here, 10-000 discusses the scope, object, and special terminology. Sections 10-100 to 10-400 discuss grounding, and as you can see here, there are 3 different types of grounding. Rules 10-500 and 10.600 discuss bonding, and Rule 10.700 discusses this new word called equipotential bonding. 10-000. As indicated in Subrule A, B, and C, Rule 10.000 applies to grounding, bonding, and equipotential bonding, and within Subrule A, grounding, we have a solidly grounded system, which is also known as a Y system, an impedance grounded system, also known as a neutral grounding system, and an ungrounded system, also known as a delta system. 10-002 and Appendix B note provides an excellent explanation regarding bonding and grounding. The overall objective for grounding and bonding is to minimize the likelihood and severity of electric shocks by establishing equipotentiality between exposed non-current carrying conductive surfaces and nearby surfaces of the Earth, and to prevent damage to property during a fault event, as follows. Subrule A. The objective of solidly grounding an electrical system and bonding its associated equipment is to establish a low impedance connection between the grounded conductor and the non-current carrying conductive parts of the system to stabilize system voltage. Subrule B. The objective of grounding an electrical system through an impedance is to limit the magnitude of ground fault currents, minimize the damage to equipment resulting from a single ground fault, and stabilize system voltage. Subrule C. The objective of an ungrounded system is to limit the magnitude of ground fault currents resulting from a single ground fault and minimize the damage to equipment on the occurrence of a single ground fault. Subrule D. The objective of bonding is to interconnect the non-current carrying conductive parts of electrical equipment and the system grounded point where one exists with sufficiently low impedance to facilitate the operation of protective devices and establish equipotentiality. And Subrule E. The objective of equipotential bonding is to establish equipotentiality. So Subrule A talks about a solidly grounded system, in other words, a 120/240 or a 120/208 volt Y system. Subrule B is an impedance grounded system. Subrule C deals with ungrounded systems, also known as a delta system. Because of different words and definition used within Section 10, it has become one of the most difficult sections of the code to understand. I thought that a good word to understand is the word system. From Appendix B, Section 0, on page 577, the word system has been further defined. Within the code, the word system is used in many different contexts. However, within the context of electrical power distribution, a system is intended to mean an electrical installation in which the energy provided by the installation to utilization equipment is derived from a single energy source. For example, an electrical installation supplied from a transformer or a bank of transformers can be considered a system. An installation supplied from a different transformer would be considered a different system. Remember when I was giving you the definitions in section 0, and I said, what section of the code contains definitions? And your likely answer would have been, well, of course, section 0. That's where all the definitions are. Well, not in this case. Within Rule 10004, there are 8 words with a specific definition that apply to this section of the code. We will explain some of the definitions in upcoming slides. Equipotentiality, the state in which conductive parts are at a substantially equal potential. Grounded conductor, in an electrical system, the conductor that is tensionally grounded. Impedance grounded system is an electrical system in which a point, normally the midpoint or neutral, is connected through an impedance device. A, to an impedance system bonding jumper, and B, by a grounding conductor to a grounding electrode or to conductive body by that extends the ground connection. Impedance system bonding jumper, a connection between the grounded side of an impedance grounding device and the non-current carrying conductive parts of the electrical system. So back to equipotentiality. Basically, the intent is to make everything of equal potential. The grounded conductor, well, in a 120-240 or a 120-208 volt system, what conductor is intentionally grounded? The neutral. Hence, we call it the grounded conductor. Carrying on with the remainder of 10004, special terminology, definitions. Separately derived system, an electrical system in which the circuit conductors have no direct connection to the circuit conductor of a supply authority system other than those established by grounding and bonding connections. Solidly grounded system, an electrical system in which a point is connected without inserting an impedance grounded device. A, to a system bonding jumper, and B, by a grounding conductor to a grounding electrode or to a conductive body that extends the ground connection. System bonding jumper, a connection between the system grounded point and the non-current carrying conductive parts of an electrical system to establish a solidly grounded system. And last but not least, an ungrounded system, an electrical system where no point of that system is intentionally grounded. Could you give me an example of an ungrounded system? And if you answered a delta system, you are correct. A system bonding jumper could be any number of ways to perform this. An example of a system bonding jumper is bonding the XO point of a 3-phase transformer to the frame of the transformer. Or it could be a bonding jumper or a bonding tab that is located in a panel board, for example, a 120/240, 120/208 volt 3-phase distribution system. The conductor that goes from the frame of the enclosure to the neutral bus is called the system bonding jumper. Equipotentiality. The primary function of bonding, as described in this item, is to provide a low impedance path to facilitate the operation of protective devices under ground fault conditions. By interconnecting the non-current carrying conductive parts of electrical equipment, bonding also establishes equal potentiality between the equipment. Once all the equipment is bolted together, grounding and bonding completed, then equal potential or equal potentiality will be established. Grounded conductor. In an electrical system, the conductor that is intentionally grounded. In these two examples, the identified neutral conductor is the grounded conductor. Impedance grounded system. In an electrical system in which a part, normally the midpoint or neutral, is connected through an impedance device, A, to an impedance system bonding jumper, and B, by a grounding conductor to a grounding electrode or to conductive body that extends the ground connection. Photo on the left is an impedance grounded system. In reality, this is a large resistor which dissipates heat when subjected to accidental fault currents. When a current reaches a predetermined value, the system will automatically shut down. The advantage of this is much like a delta system, but contains a neutral conductor. This is used in heavy industrial situations where a ground fault will not trip the overcurrent device, but also trained maintenance people are on staff to fix any problems. The photo on the right is of a one-line diagram, which is critical to keep and maintain on a work site. 10004, separately derived system. An electrical system in which the circuit conductors have no direct connection to the circuit conductors of a supply authority system other than those established by grounding and bonding connections. The definition of separately derived system has been defined in Rule 10004 with additional excellent information in Appendix B, located on page 591 of your codebook. Separately derived system. All transformers, except autotransformers, are considered a separately derived system because the primary supply does not have any direct electrical connection to the secondary. An autotransformer, as you can see by the photo on the right, is not a separately derived system because both the primary and secondary windings are connected to a common winding. From page 591 of Appendix B, here is more of an explanation of a separately derived system. A separately derived system has no direct electrical connection to a supply authority system. Examples of separately derived systems include generators, batteries, converters, inverters, isolation transformers, and solar photovoltaic systems, provided they have no direct electrical connection to a supply authority system. The earth, metal enclosure, metal raceways, and bonding conductors may provide incidental connection between the supply authority system and the separately derived system. In addition, a common grounding electrode can be installed for multiple separately derived systems as well as a supply authority system. Two or more separately derived systems can be commonly connected either by direct connection of phase conductors and or grounded conductors and still be separately derived if they do not connect to the corresponding conductors of a supply authority system. Continuing on from page 591 of Appendix B, here's more of an explanation of separately derived system. Where the grounded conductor of two or more separately derived systems terminate at a common tie point, the system bonding jumper and grounding conductor connections for all the systems are made at that common tie point. When a system has a common connection with a supply authority system through phase conductors and or grounded conductors, it is not a separately derived system. Examples of that are an emergency standby generator connected to buildings load via a transfer switch that does not switch the grounded conductor, or an interconnected power production system under the scope of Section 84. The grounding requirements for such systems are met by the grounding connection of the supply authority system to which they are conductively connected. Further information on a separately derived system. Here are two examples of a separately derived system. Every time you install a transformer, you are creating a separately derived system. An autotransformer, however, is not a separately derived system because both the primary and secondary windings are connected to a common core. If you notice in each of these photos, you have a delta Y transformer. The primary and secondary windings are not connected to a common core. Hence, anytime you have this type of setup, you are creating a separately derived system. For more information on this, please consult Section 10, Appendix B drawings for excellent explanations and drawings. System bonding jumper, a connection between the system grounded point and the non-current carrying conductive parts of an electrical system to establish a solidly grounded system. Here are two examples of a system bonding jumper. The photo on the left, in this situation, the system bonding jumper is part of a panel board and is known as the green or brass colored screw. Some panel boards will provide a copper ribbon between the grounded conductor and the enclosure frame. Photo on the right, as you can see, this is a transformer. The grounding conductor terminates at the transformer XO point, but the green conductor from the transformer XO to the transformer frame is known as the system bonding jumper and is sized in accordance with Table 16 and Appendix B Note Rule to 10614, Subrule 1 and 3A. Ungrounded system, an electrical system where no point of that system is intentionally grounded. Photo on the left, in this situation, you would ground to the frame of the service enclosure only, and then provide a bonding conductor for the rest of the electrical system downstream. There is no XO point to ground, so on a delta system, when you install your grounding electrode with your grounding conductor, you terminate the grounding conductor on the frame of the enclosure. Photo on the right, and no, this is not a mistake, and no, there are no burnt out lamps in this situation. Two phases have actually gone to ground. The interesting thing about this photo was that two separate businesses were connected to the utility's Delta connected transformer. Each owner had a ground fault which indicated on each other's ground fault indicating lights. That's how sensitive ground fault indicating lights actually are. they will actually detect a ground fault from a neighboring property or a neighboring customer. (2015) Canadian Electrical Code Rule 10-200 has been moved to 10-100 and has been significantly revised to now read, "There shall be no objectionable passage of current over the grounding conductor." From Appendix B note, which now states, "Any neutral currents in grounding conductors are considered objectionable." Corrective action for neutral current on grounding conductors may require that A. One or more of the grounds be abandoned, B. The location of the grounds be changed, subrule C. The continuity of the conductor between the grounding connection be suitably interrupted, or D. Other effective actions to be taken to limit the current. Currents in a grounding conductor that are not considered objectionable are those that may occur under normal operation, such as temporary currents resulting from a grounded fault or the induced current from adjacent single conductors. The 2015 Canadian Electrical Code, Rule 10-806, discussed installation of system grounding conductors. Subrule 1 read, "The grounding conductor for a system shall be without joints or splices throughout its length, except in the case of bus bars, thermite-welded joints, and compression connectors." Rule 10-116 of the 2018 Canadian Electrical Code now replaces the former 10-806. 10-116 Installation of grounding conductors. Subrule 1. The grounding conductor shall be electrically continuous throughout its length. Subrule 2. Where necessary, devices to control the effect of stray earth current shall be permitted to be connected in series with the grounded conductor. Subrule 3. A grounding conductor shall be protected from damage, A. Mechanically or by location. Subrule 4. Raceways or sleeves constructed of magnetic material used to enclose grounding conductors shall be connected to the grounding conductor at both ends. And Subrule 5. A grounding conductor installed in the same raceway with service conductors shall be insulated, except that an uninsulated grounding conductor shall be permitted where the length of the raceway, A, does not exceed 15 meters between pull points, and B, does not contain more than the equivalent of 2 90-degree bends between pull points, or 180 degrees. So what does that now mean? The grounding conductor is no longer required to be one continuous unbroken run that is free of splices. You no longer require bus bars, thermite-welded joints, and compression connectors, splicing, and as a matter of fact, split bolts are now considered acceptable. Devices used for connecting and terminating of grounding conductors would be required to be approved for the purpose by the general requirements of this code. A common grounding conductor from multiple systems would be permitted, and there is no change to grounding conductor size or the allowance of aluminum grounding conductor. (10-116) Split bolts will now be considered acceptable for splicing grounding conductors. However, in this case, what do you notice about the two conductors that are installed here? One is actually smaller than the other. Please keep in mind, For copper, number 6, copper is the minimum grounding conductor size. In this example, the compression connection is correct. However, the grounding conductor is actually too small. 10-210, grounding connection for a solidly grounded AC system supplied by the supply authority. The grounded conductor of a solidly grounded AC system supplied by the supply authority shall A. be connected to a grounding conductor at one point only at the consumer service. Subrole B. have a minimum size as specified in Subrole 1 for a bonding conductor. 2. For a neutral conductor where the grounded conductor also serves as a neutral. Subrole C. Be connected to the equipment bonding terminal by a system bonding jumper. And D. Have no other connection to the non-current carrying conductive parts of electrical equipment on the supply side or the load side of where the grounding connection is made. This means that regrounding at a secondary building fed from the same service, will no longer be permitted for any type of building, not just buildings housing livestock as per the 2015 Canadian Electrical Code Rule 10-208. Grounding is performed at one point only. 10-210, grounding connection of a solidly grounded AC system supplied by the supply authority. In this photo, there are two examples of where the service may be grounded. The photo on the left is the consumer service grounded at the meter mounting device. And the photo on the right is the consumer service grounded at the service box. The right picture, if the grounding is completed in the service box, then the identified conductor must have no other connection to the non-current carrying conductive parts of electrical equipment on the supply side or on the load side of where the grounding connection is made. Therefore, an isolation kit must be installed in the meter base for the identified conductor. The picture on the left, caution must be used. Presently, there is no CSA standard for grounding in a single meter base. Therefore, this method is currently not approved. If you require further information, please consult your local authority having jurisdiction and your local utility for additional information. 10-210, grounding connection for a solidly grounded AC system supplied by the supply authority. Continuation. In accordance with 10-210, the grounded conductor of a solidly grounded AC system supplied by the supply authority shall be connected to a grounding conductor at one point only at the consumer's service. In both photos, neutral support cable is installed overhead from an electrical room to an outbuilding. Neutral support cable does not contain a bonding conductor. Neutral support cable normally contains either 2 or 3 ungrounded conductors and a bare identified conductor. Therefore, regrounding was re-established at an outbuilding. Except for buildings housing livestock, prior editions of the code permitted regrounding at an outbuilding. Not anymore. In these examples, any outbuilding cannot be regrounded, and a separate bonding conductor must be installed with the feeder conductors. This is not an issue if TEC or ACWU is installed underground because a bonding conductor is integral with the cable. Neutral support cable, however, poses a problem in this situation. 10.210. Grounding connection for a solidly grounded AC system supplied by the supply authority. Continuation. In accordance with 10.210, the grounded conductor of a solidly grounded AC system supplied by the supply authority shall be connected to a grounding conductor at one point only at the consumer service. So the photo on the left is an outbuilding containing livestock. The barn is subfed from a main electrical room. A bonding conductor is installed with the neutral support cable to the panel board. We do not reestablish a ground due to the possibility of tingle or step voltages sensed by livestock. The photo on the right, the feeder installed in conduit from the main electrical distribution center does not contain a bonding conductor, and a ground is reestablished. This is not permitted anymore. Ten 212. Grounding connection for a solidly grounded, separately derived AC system. A delta Y transformer creates a new separately derived system. Grounding may now be accomplished by the bonding conductor included in the primary supply. Now, Subrule 1 states, except as permitted by Subrule 2, the grounded conductor of a solidly grounded separately derived system shall A. be connected to the equipment bonding terminal by a system bonding jumper, 1. at the source, 2. at the first switch controlling the system, or 3. at the tie point where two or more system terminates at a tie point. Subrule B, be connected to a grounding conductor at the same point on the separately derived system where the system bonding jumper is connected, and C, have no other connection to the non-current carrying conductive parts of electrical equipment on the supply side or the load side of the grounding connection. Subrule 2, a separately derived AC system operating at 750 volts or less shall be permitted to be grounded by the system bonding jumper that is connected to the bonding conductor included in the primary supply. So from the photo on the right, as you can see, the grounding conductor, the bonding conductor and the grounding conductor can be one of the same. For further information, consult the Appendix B drawings on Section 10. 10.214. Grounding connection for portable generator assemblies and vehicle-mounted or mobile generators. A portable generator assembly shall not be required to be connected to a grounding electrode if the generator has the neutral bonded to the frame. A mobile or vehicle-mounted generator shall not be required to be connected to the grounding electrode under the following conditions. The generator does not exceed a low voltage rated output. The generator has the neutral bonded to the frame. The conductive frame of the generator is connected to the conductive frame of the vehicle by an equal potential bonding conductor. Subrule D, the generator supplies only electrical equipment installed on the vehicle, electrical equipment that is cord or plug connected through receptacles mounted on the vehicle or on the generator, or any combination of the equipment specified in items 1 and 2, and the non-current carrying conductive parts of the electrical equipment referred to in item D are supplied by a circuit incorporating a bonding conductor. CSA Standard 22.2 number 100 specifies the construction requirements for generators, including portable generator assemblies. A portable generator assembly consists of a prime mover, a generator, overcurrent devices, and output receptacles that are assembled and connected on a common machine frame, and is capable of being carried or moved about by personnel. A portable generator assembly is rated at not more than 12 kilowatts and not more than 240 volts, and is intended to be used as an isolated system for the supply or cord-connected electrical equipment. As a condition of approval of certain types of electrical equipment, such as portable generators, the manufacturer supplies instructions pertaining to its installation and operation. It is important that the end user closely follow the instructions supplied by the manufacturer to fill the terms of the approval agreement. So for additional information, read the Appendix B note on 10.214. 10.214. Grounding connection for portable generator assemblies and vehicle mounted or mobile generators. Here are two photos. The photo on the left is a mobile generator which is towable behind a vehicle, and the photo on the right is a portable generator. Assembly sometimes found on some work trucks. Please read Appendix B note on page 604 for additional information. 10.302. Impedance grounded system. Ungrounded conductors of an impedance grounded system shall be insulated to the nominal 10.302. Impedance grounded system. Ungrounded conductors of an impedance grounded system shall be insulated to the nominal line-to-line voltage of the system. The integrity of the impedance grounded system shall be monitored and shall have an audible and visual alarm that corresponds to the occurrence of A. Ground fault on current carrying conductors, including the neutral conductor where line to neutral loads are served. B. A ground fault on the conductor connecting the impedance grounding device to the source, and subrole C. A loss of continuity on the impedance grounding circuit from the system source through the impedance grounding device to the grounded non-current carrying conductive parts of the electrical system. So in this photo, if the impedance ground resistance detects current on any of the conductors or loss of continuity, an alarm will ring. 10.400. Ungrounded systems. DC or AC systems shall be permitted to be ungrounded, provided that the system is A. Equipped with suitable ground fault detection, and B. Maintained by qualified persons. Subrole 2. On the occurrence of a ground fault, the ground fault detection shall activate a signal or audible alarm to indicate the presence of a ground fault. The alarm required by Subrole 2 and any extra, in other words, redundant alarms, if installed, shall be clearly labeled as to their purpose, clearly enunciate the status of the system to persons monitoring the system, and continues signaling until the condition has been corrected. Subrule 4. Extra low voltage DC and AC systems shall be permitted to be ungrounded without having to comply with the ground fault detection requirements specified in subrules 1 and 3. So what this rule is specifying is not only do you have to have the ground fault indicating lights, you have to have an audible alarm so that maintenance personnel can actually hear that there's a problem and then correct the situation as deemed necessary. 10-500, bonding, general. Guess what? 10-500 is back. In the prior 2015 Canadian Electrical Code, this section was reserved for future use. 10-500 deals with bonding. 10-500, current over bonding conductors. See Appendix B. There shall be no objectionable passage of current over a bonding conductor. 10-502, where a non-conductive protective coating such as paint or enamel is used on conductive equipment, conduit, coupling, or fittings, such coating shall be removed from threads and other contact surfaces or penetrated to ensure a good electrical connection at the point of bonding. 10-504, dissimilar metals. Where dissimilar metals that are not compatible cannot be avoided at bonding connections, connections shall be made using a method or material that will minimize deterioration from galvanic reaction. 10-506, continuity of bonding conductors. No automatic cutout or switch shall be installed in the bonding conductor of a wiring system unless the opening of the cutout or switch disconnects all energy sources. So going back to these prior rules, surfaces used for bonding must be clean. Caution should be used when dealing with dissimilar metals because of galvanic reaction or galvanic action. And the bonding conductor shall have no cutout or switch unless there's a switch that disconnects all energy sources. 10-604, bonding continuity for service equipment. The bonding continuity for service raceway, cable armor, cable sheath, and all service equipment enclosures containing service conductors, including meter fitting, boxes, or the like, shall be assured by threaded couplings and threaded connectors to the conductive enclosure, with joints made up tight where rigid metal conduit is used. Couplings and connectors made up tight where electrical metallic tubing is used. And Subrule C, bonding bushings supplemented with a bonding conductor where the connection to the enclosure is made using standard lock nuts. Subrule 2, notwithstanding Subrule 1C, a bonding bushing shall not be required for cable assemblies incorporating an integral bonding conductor in continuous contact with the armor cable, provided that the internal bonding conductor extends from the cable and connects to the service equipment. So a little hint here, TEC and ACWU will require a bonding bushing for the connection at service equipment, since the internal bonding conductor is actually isolated and does not make contact with the armor. Please consult your local authority having jurisdiction to determine the number of bonding bushing that are required. Some authority having jurisdictions are requiring bonding bushings at both ends, and some are requiring bonding bushings at one end only. Please be careful of this rule and consult your local authority having jurisdiction for further information. 10.604 Bonding Continuity for Service Equipment, Continuation. 10.604 Subrule 2 is new. The bonding conductor of TEC and ACWU does not make contact and does not make continuous contact with the cable armor. Therefore, bonding bushings are required. On TEC, the bonding conductor is isolated from the cable armor due to the internal plastic jacket. And ACWU, the bonding conductor is isolated from the cable armor due to the internal paper jacket, and also how the bonding conductor is wrapped tightly between the conductors of the cable. On a side note, are you familiar with the abbreviation ACWU? Do you know what it actually stands for? Hint, 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 hint. Aluminum cable wet underground. And how, if you did not know the difference between TEC or ACWU, if you just looked at the two cables, how could you determine which cable is TEC and which one is ACWU? TEC has the internal rubber jacket around the conductors, whereas ACWU wraps their conductors in paper. That's how you can tell the difference between TEC and ACWU. 10.606 Bonding continuity at other than service equipment. Bonding continuity of metal raceway, metal sheath cable, or armor cable shall be assured by one of the methods specified in Rule 10.604, Subrule 1, or by using A. Standard box connectors made up tight. Subrule B. 2 lock nuts, one inside and one outside of the box and cabinet. Or C. 1 lock nut and a metal conduit bushing, provided that the bushing can be installed so that it is mechanically secure and makes positive contact with the inside surface of the box. Subrule 2. Reducing washers shall not be used to maintain the bonding continuity of the wiring system. Once again, reducing washers shall not be used to maintain the bonding continuity of the wiring system. Now, can you tell me what you are now going to install along with the reducing washers? Hint, hint, hint. Bonding bushings. So once you install reducing washers, you have to install bonding bushings. 10.606 Subrule 2 Bonding continuity at other service equipment, continuation. This is a subpanel located in a dwelling unit. So it is not service equipment, it is a subservice. However, the use of reducing washers shall not be used to maintain the bonding continuity of the wiring system. A bonding bushing is now required to satisfy the intent of this rule. 10.614 Size of system bonding jumper or bonding conductor. See Appendix B. The two asterisks noted in red denotes students must use caution when using this rule, as important information is listed in Appendix B notes. The next 6 slides deal with Rule 10.614. This rule has been completely rewritten, and caution must be used when dealing with this rule, especially Subrule 1 and 3a. Subrule 1. The size of a field-installed system bonding jumper, and by now we should all know what a system bonding jumper is, shall be not less than that determined in accordance with Table 16 based on the ampere rating or setting of the overcurrent device protecting the ungrounded conductors. Subrule 2. The size of a bonding conductor installed in accordance with 10.604 at service equipment shall be not less than that determined in accordance with Table 16 based on the allowable ampacity of the largest ungrounded conductor. Subrule 3. The size of a field-installed bonding conductor installed in other than service equipment shall be not less than that determined in accordance with Table 16, based on the overcurrent device protecting the ungrounded conductor, or the allowable ampacity of the largest ungrounded conductor for installations where the size of the circuit conductor is increased to compensate for voltage drop. 10.614. Size of bonding jumper or bonding conductor. Continuation. Although the information provided in Subrule 4 through 7 are important, these rules were already discussed in prior code editions. However, Subrule 4, the size of a field-installed bonding conductor installed with each group of parallel conductors run in separate raceways or cables shall be in accordance with Subrule 3 divided by the number of groups of parallel conductors. Subrule 5. Notwithstanding Subrule 2, 3, and 4, the bonding conductor shall not be required to be larger than the current carrying conductors. Subrule 6. A metal raceway that is permitted to be used as a bonding conductor shall be considered to meet the requirements of this rule. And Subrule 7. A bonding means that is integral to a cable assembly shall be considered to meet the requirements of this rule. Table 16. Minimum size of field-installed system bonding jumpers and bonding conductors. See Rule 10.614. Table 16 replaces Table 16A and Table 16B, which have now been deleted. On the top left side of the table, we have ampere rating or setting of overcurrent device protecting conductors, equipment, etc., and allowable ampacity of largest ungrounded conductor or group of conductors. On the left side of the table, we have ampere rating with the notation not exceeding. On the top of the table, we have either wire or bus, your choice, what are you using? Below that, we have your choice of either copper or aluminum, wire or bus bar, and below that, are you using wire or bus, and what are their sizes? So now, for example, if you are trying to determine the size of a bonding jumper for the service on for a 200 amp service, you would just look over at 200 amps, slide to the right, and if you are using wire, you're using a number 6 copper conductor or a number 4 aluminum conductor. So you do not use Table 41 in this case. you use table 16. A little later, we will be discussing the size of a bonding conductor relating to a transformer. 10.614, size of system bonding jumper or bonding conductor. See Appendix B. Subrule 1. The size of a field-installed system bonding jumper shall not be less than that determined in accordance with Table 16, based on the amp rating or setting of the overcurrent device protecting the ungrounded conductors. Subrule 2. The size of a bonding conductor installed in accordance with Rule 10.604 at surface equipment shall be not less than that determined in accordance with Table 16 based on the allowable ampacity of the largest ungrounded conductor. Subrule 3. The size of a field-installed bonding conductor installed at other than service equipment shall be not less than that determined in accordance with Table 16 based on the overcurrent device protecting the ungrounded conductor or the allowable ampacity of the largest ungrounded conductor for installations where the size of the circuit conductor is increased to compensate for voltage drop. The next 4 slides discuss Rule 10.614. 10.614 Subrule 1 states that a field-installed system bonding jumper is determined in accordance with Table 16 and based on the amp rating or setting of the overcurrent device. 10.614 Subrule 3 states the size of a field-installed bonding conductor installed at other than service equipment shall be not less than that determined in accordance with Table 16 based on A, the overcurrent device protecting the ungrounded conductors. And by now, we all know that a system and field-installed bonding jumper is, and we are going to relate this to a transformer question coming up. But first, 10.614, size of system bonding jumper or bonding conductor. Appendix B notes. These notes provided for in Appendix B will assist you in determining the system bond jumper or bonding conductor size. 10.614. The principal purpose of the bonding conductor is to provide a low impedance path for fault current and to facilitate the operation of overcurrent protective devices, in addition to serving as equal potential bonding connection. So question, when they talk about the fault current and facilitate the operation of the overcurrent device, what does the word facilitate mean? To operate. In other words, they want to make sure that the overcurrent device will operate. That's what facilitate means. Rule 10.614, Subrule 1 and 3A. When the system or circuit conductors on the secondary side of the transformer are protected only by the overcurrent device on the primary side, the voltage ratio of the transformer is applied to the overcurrent device rating in applying column 1 of Table 16. So, question. We'll get to that question in a second. Next rule, 10.614, Subrule 3B. When the size of the circuit conductors is increased to compensate for voltage drop due to the circuit length, the ampacity of the conductor exceeds that required for the connected load of the rating of the overcurrent protective device. The bonding conductor needs to be increased proportionally to minimize the impedance of the bonding path and to facilitate the operation of the overcurrent device. The size of the bonding conductor is based on the circuit conductor allowable ampacity given in column 2 of table 16 to compensate for conductor length. So you can either use the overcurrent device or the conductor size. However, if your conductor is increased in size due to voltage drop, then the size of the bonding conductor must be increased proportionally. Now going back to 10614, my question is, when you read that statement, when the system or circuit conductors on the secondary side of the transformer are protected only by the overcurrent device, on the primary side, the voltage ratio of the transformer is applied to the overcurrent device rating in applying column 1 of table 2. So my question is, what is the voltage ratio of a 600 to 120 208 volt transformer? Well, all you do is you divide the primary into the secondary. So 600 divided by 208, and you come up with 2.88. That is a very important number to remember, and we will be using that number, 2.88, in a few minutes. 10614, size of system bonding jumper or bonding conductor. See Appendix B notes. So here's a question for you. Determine the size of copper system bonding jumper and bonding conductor for a dry type 112.5 kVA 600 to 120 208 volt step down transformer. Primary overcurrent protection only. There is no secondary overcurrent protection provided in this situation. Use Rule 10.614, Subrule 1 and 3A, Appendix B notes, and Rule 26.254, Subrule 1 and 3 will also be used. First step, the voltage ratio between the primary transformer to secondary is 600 volts divided by 208 volts equals 2.88. So we want to determine the maximum primary overcurrent protection permitted. In this case, we take the 112.5 kVA divided by 600 times root 3 equals 108.2 amps. Now, we have to increase our conductor size a minimum of 125%. So 108.2 amps times 125% gives us 135.32 amps. We use rules 26.254, subrule 1. If we decide to lower our overcurrent device down to 125 amps, we then multiply our primary overcurrent protection by 2.88, which now equals 360 amps. In accordance with table 16, we go to column 1, and that tells us we use a number 3 copper conductor. If we decide to increase our overcurrent device in accordance with 26.254 subrule 3 to 150 amps, because 135 is not a standard overcurrent device, we multiply the 150 amps by 2.88, and we now come to 432 amps. We then look at table 16, column 1, and our conductor is now a number 2 copper. So do you see how nasty this rule can be? Just by increasing the overcurrent device, we now have to use a larger conductor. 10614. Size of system bonding jumper or bonding conductor. See Appendix B notes. So from the prior question, the system bonding jumper, circled in red here, will either be a number 3 or number 2 copper conductor. The size depends upon what you size your primary overcurrent is. Once again, if your primary overcurrent protection has been reduced down to 125 amps, a number 3 copper conductor is permitted. However, if you upsize the overcurrent device to 150 amps, your system bonding jumper is now a number 2 copper conductor. 10700 is not new to the BC Electrical Code, but the heading Equal Potential Bonding clearly is. 10700 subrule A through F inform you as to what non-electrical, non-current carrying conductive parts require equal potential bonding. So 10700 equal potential bonding of non-electrical equipment. The following parts of non-electrical equipment shall be made equal potential with the non-current carrying conductive parts of electrical equipment. Subrule A, the continuous metal water piping system of a building supplied with electric power. So if a dwelling unit or building has continuous metal water piping, it must be bonded. The continuous metal wastewater piping system of a building supplied with electric power. So once again, if a building has continuous metal wastewater piping system, it must be bonded. However, question, how do you bond cast steel, which has a rubber coupling every 10 to 15 feet or every joint? Please talk to your local authority having jurisdiction on that question. Subrule C, the continuous metal piping, gas piping system of a building supplied with electric power. The gas line must be bonded. However, use extreme caution on this. Bonding must be completed on steel piping. You do not bond the flexible yellow stainless steel piping. Problem that may result if you do bond on the flexible piping is you are going to damage the piping and thereby allowing gas to escape. So you only bond on the rigid steel portion. Subrule D, raised floors of conductive materials with electric wiring under a floor. Subrule E, the conductive metal parts of structures that livestock access. In other words, barns. Subrule F, metal tower and station structures of passenger ropeway, passenger conveyors, and material ropeways. 10702, conductors for equal potential bonding shall be permitted to be installed as open wiring, provided that they are adequately secured. Subrule 2, where installed in structural members, conductors for equal potential bonding shall be installed in the same manner as non-metallic sheath cable, except that they do not require bushed holes where run through metal studs. 10704, material for equipotential bonding conductors. Equipotential bonding conductors shall be of material permitted for grounding conductor or for bonding means. 10706, equipotential bonding connections to non-electrical equipment. Equipotential bonding connections to non-electrical material shall be made mechanically secure and be suitable for the condition to which they are subjected. In other words, if you are using copper or aluminum as your bonding conductor, your connectors must be approved for the purpose. So they must be approved for either copper or aluminum use. If you're using a connector in an outdoor wet location, the connector that you used must be approved for the location. 10.708 Equipotential bonding conductor size. Except as permitted by Subrule 2, the size of an equipotential bonding conductor shall be not smaller than number 6 AWG if of copper, or number 4 AWG if made of aluminum. Now, Subrule 2, the size of an equipotential bonding conductor installed as concealed wiring and mechanically protected shall be permitted to be a minimum size of number 10 copper or number 8 aluminum. When doing or using Subrule 2, please consult your local authority having jurisdiction for further information. So back to 10.700 equipotential bonding. As you can see here, here's a picture of a premise, whatever it happens to be. As you can see, the gas line, which is marked in yellow, has a number 6 AWG copper with approved clamps. The water line next to the hot water tank is also picked up with a number 6. Underneath the sink down below, there is a jumper for a complete metal wastewater piping system. And to the left, we have domestic cold water, which appears to be copper as well. They use a number 6 for that as well. But use caution when dealing with a continuous metal wastewater piping system. If you have further questions, please consult your local authority having jurisdiction for further information. And in this photo here, we have a barn housing livestock. The stanchions, in other words, what the cows put their heads through, all of those stanchions will require bonding of some sort or some type. The problem with animals that have hooves is they actually make contact to the ground in 5 points. In other words, 4 hooves and what's called a snout. If there is any difference of potential, believe me, horses, cows, livestock will sense a difference of potential in voltage throughout the ground. They have been known to cause problems afterwards where, for example, a cow will not be producing as much milk because of the electric current that's going through the ground. The animal is actually being shocked or electrocuted. Although we can't feel it, the animals can. So once again, equipotential bonding, especially for livestock, is very critical. So that concludes section 10. I hope you've enjoyed it. It's a big section, lots of changes. And when in doubt, please consult the drawings in the back of Appendix B. They provide additional excellent resources that in actual fact should have been in section 10, but now you know why they lost 5 pages of section 10 because they moved it over to Appendix B. Take care and have yourself a good day. Goodbye.